All right. Well, hi, everybody. We're here to do a little pre-lab for the carbon-13 NMR experiment. I say we're here because
I'm here too.
Dr. Riley is here too. We're exercising some social distancing to keep safe with all that's going on. So what we want to do is just give you a little pre-lab like we would during the normal lab meeting for the carbon-13 NMR experiment. And so as part of this, I like to go back and sort of review where we've been and put the carbon-13 NMR in perspective with what we've already learned with sort of using spectroscopy and instrumentation techniques to solve the structures of organic molecules. So it started off with mass spectrometry, otherwise there is MS. And from the mass spectrometry, the big information that we got from it was the molecular weight, which we got through the molecular ion. And so we have the molar mass of the compound. If you recall from that, we could generate formulas where we'd look at how many carbons would go into the molecular weight and then fill the rest of the weight with hydrogens. We could look at oxygen as a possibility, nitrogen as a possibility. And then once we had some possible formulas, we could further calculate unsaturations. And
Well,
that would give us...
How would we know? Oh, sorry, I didn't mean to interrupt. I should say, how do we know if we have an oxygen or not potentially? What would help us figure that out?
Yeah, well, this is how the different spectroscopic techniques would play against each other, where you might take a quick look at your infrared spectrum to see if there's evidence of an OH in that area around 3300 or the carbonyl at around 1700.
Oh yeah,
So,
no, I remember.
We'll review IR in just a moment here as well. So the unsaturations are going to give you your first kind of hints of requirements for structure, whether there are rings or multiple bonds necessary for that formula. From there, we learned about infrared spectroscopy. And what IR really told us about bonds in our structure, and particularly the bonds associated with functional groups. Which is what Dr. Roy was getting at, where you take a quick glance at your IR, you could see usually pretty quick evidence for the presence of things like arenes, alkenes, alcohols, carboxylic acids, any of the carbonyl compounds, and that would inform some of the formula work you might do from your mass spec data. With the mass spectrometry, I should remind, we do get fragmentation data, but we usually don't wrangle with that until after we've got a structure in hand, so that's why I left it off for now. And then a couple weeks ago, we talked about proton NMR spectroscopy. And that was a technique that we saw informed us as to the carbon-carbon and carbon-hydrogen bond connectivity in a molecule, and certainly that's powerful information if you're trying to solve that structure. If you recall, we got 4 types of information from that NMR. The first was the number of signals. And that correlated with the number of different types of hydrogen within the molecule. We had the chemical shift. And that had to do with where the signal occurred in the spectrum. If you recall, the useful range was from about 0.9 parts per million to about 12 parts per million, and where a signal occurred in that range would inform you as to what type of hydrogen it likely was, and what type of structural units it was likely nearby. And we had a data table that we used to help us correlate that information. The third feature was integration. This had to do with the area underneath the signal within the spectrum, and that's proportional to the number of hydrogens causing that signal. And so one of the key features there is that the sum of all the integration values in the spectrum have to add up to equal the number of H's in your formula. So some ways that the proton NMR can help you confirm which formula you're working with if there's more than one possibility. And then the last feature was the spin-spin splitting or coupling. This had to deal with the shape of the signal, whether it was a singlet, a doublet, a triplet, or a multiplet of some type or another. And we had a little formula that helped us out with that, where the peaks was equal to the number of neighbors plus 1, where neighbors are defined as the hydrogens on adjacent carbon atoms within the structure. So that's kind of where we've been with spectroscopy for identifying organic molecules up to this point. Anything to add, Dr. Riley?
Not really. We sometimes call it coupling splitting. I think that's what it kind of refers to it a little bit more in the, but it's the same idea.
Yep.
So what do we have to add to that?
Well, today we're going to be talking about carbon-13 NMR. And so looking at the carbon nuclei within our molecules rather than the hydrogen nuclei. Here specifically the carbon-13 isotope of carbon is the one that we can look at. And so with carbon-13 NMR, there are parallels with proton NMR, but also distinct differences. As far as features comparing it to proton NMR, 2 of the 4 features that we see in proton NMR we make use of in the carbon-13 NMR. The first one is the number of signals. And so similar to the proton NMR, the number of signals in the carbon-13 NMR is the number of different types of carbon in the molecule. And so in that regard, we'll have a pretty similar process of inspecting structures for different types of carbon. And then the second feature that we have is chemical shift. And so again, similar to the proton NMR, chemical shift has to deal with where the signal for a given type of carbon occurs within the spectrum, and that correlates then with what type of carbon it might be. Now, in your manual, around page 111 or so, we've got a NMR data table. So I'm bring this up to the camera. You can find yours. But you can see it's similar to the one we use for proton NMR, where it gives the type of carbon and then the chemical shift of that type of carbon. Now, one difference here is the range for carbon-13 NMR goes from about 5 ppm out to about 220 ppm. So it's a much broader range in the proton NMR, but similar in makeup where different types of carbons are going to occur in different ranges along that spectrum. Integration goes away in the carbon-13 NMR, and so all that means is a signal that's short and a signal that's tall could be both caused by the same number of carbons. And that has to do with something called relaxation time, how long it takes a nuclei to relax back to its equilibrium state before it gets detected again. Carbons tend to have very long relaxation times. Couple that with the fact that carbon-13 is about 1% of carbon, you have very, very, very long experiments if you try to get the integration data. So instead of that, we collect data on the samples very frequently, oftentimes 100 or 1,000 scans, and in so doing, we sacrifice the integration data. The coupling data is also removed from the spectrum. The standard carbon-13 NMR is what's called a proton decoupled carbon-13 NMR, and that's where the splitting that would occur between the hydrogens that are on a carbon and that carbon signal is purposefully removed. So all of the signals show up as singlets in the carbon-13 NMR. Now the exercise that you're going to be doing today also includes what's called depth NMR. And through the depth NMR, there's 3 experiments that we do, and that's going to allow us to recapture that information that we lose by removing the splitting. So we will be able to tell how many hydrogens are attached to each different type of carbon within our molecule. All right, we're going to take a pause for a second, and then we'll come back and talk a little bit more about carbon-13 NMR. All right, what we're going to do now is take a look at an example molecule and kind of go through the process of looking at the features of the carbon-13 NMR and then sort of predicting what that NMR spectrum might look like if we actually saw it. So here we've got a molecule that would be called isopropyl propionate, so it's an ester. And one of the features of carbon-13 NMR would be the number of signals. So how many signals would we expect to see in the carbon-13 NMR? And this process will be similar to what you did with proton NMR, where at first glance you'd probably look for the different types of carbons based upon how many hydrogens that are there. So for instance, I look here, this is a CH2. It's the only CH2 in the structure, so that's a unique type of carbon within the molecule. So that's going to give us 1 signal. Put a square around that one. We've got the carbonyl carbon here that's got no H's attached to it. That's a different type of carbon, the only one in the structure that has no H's attached to it. So I'll put a triangle around that one. Over here we've got the C with 1 H, the methine. And so that's unique, it's the only one of this carbon that's different. So I'll put a circle around that one. And now at the end of the structure over here, and the end of the structure over here, we've got 3 methyl groups. So just like with proton NMR, this is where you have to decide, are all these methyl groups the same, are some of them the same, and some of them different, to determine how many signals would be there. And so in this case, we've got the methyl group at the end that's bonded to the CH2. That's different than the methyl groups at this end that are bonded to a CH. And so we'll put a little heart around that one. And then the 2 methyl groups here that are bonded to that same CH, they would be identical to each other, and so they would cause 1 signal. And we could put a clover, a little Lucky Charms thing here around those. So this molecule's carbon-13 NMR spectrum, we would expect to give 1, 2, 3, 4, 5 signals. Number of signals 5. Now, if we're doing this for the proton, what you'd want to know is we would not have identified this as a signal in the proton NMR because there's no hydrogens attached to that position. So that's one of the things to look out for as you're reflecting back on that you would have ignored the positions in the molecule that didn't have hydrogens before. If those are carbon positions, we would count them now. The next thing we do then is look at the chemical shift. So where in that spectrum between 5 and 220 would these given signals occur? And so if you get out your data table, we can look at the different types of carbons here and kind of identify what range they would be in. So if we look at that first methyl group, the heart signal, that's going to fall into the aliphatic category. So aliphatic in the carbon-13 NMR runs from a range of about 10 to about 50 ppms. So that methyl group is too far away from any fancy structural units to be affected. So this is kind of where our signals start off, is in that 10 to 50 range, and if they get shifted toward the end of that range or higher than that range, that's where they're next to something fancy or part of some functional group. The CH2 here, the square signal, well, that's next to the carbonyl, and in the proton NMR we would have saw that as a different signal. In the carbon-13 NMR, they aren't distinguished quite as well. So that one's going to be in the 10 to 50 range as well. So that's one of the limitations of carbon-13 NMR, is some of the carbons aren't distinguished quite as well from each other as the protons would be in the proton NMR. We get to the carbonyl carbon signal there, the triangle. Now that one is a carbonyl, and in general they occur between 160 and 220, and they're broken up depending upon what class of carbonyl compound they are. So the carboxylic acids and their derivatives tend to be lower in that range, between about 160 and 185. And then the aldehydes and ketones tend to be higher in that range, typically between 180 and 220. So here our functional group is an ester, so we'd expect that one to be between about 160 and 185 ppm. So shifted way down to the left in the spectrum. Going over here, we've got our CH signal, our methine. That's directly bonded to an oxygen. And now the carbon-13 NMR, being bonded to that oxygen does tend to cause a shift downfield, like you saw in the proton NMR. And here the range on that is 30 to 80 ppm. Now note there is significant overlap between 10 to 50 and 30 to 80. So of these aliphatic signals, we probably expect that one to be shifted furthest to the left in the spectrum. And then lastly, we've got those other two methyl groups that are equivalent, sulfur signal. And those would be aliphatic far enough away from that oxygen to not be affected. So they'd be in that 10 to 50 ppm range as well. So the basic spectrum, we'd expect to see 5 signals. We'd expect 3 of them to be in that aliphatic range between 10 and 50, 1 of them to be shifted down a little bit further between 30 and 80, and then 1 of them to be shifted down significantly, that carbonyl, between 160 and 185. Now, where the depth experiment comes into play is there's 3 different depth experiments, and they're going to give us additional information about these different carbon atoms. What we typically do when we get this data is we get what's called a stacked plot, and it's where we'll stack the standard carbon-13 NMR with the depth experiments on top of them. So if I would draw a scale here for the proton decoupled spectrum and have this be 0 and this be 220, we might have our signal down here between 160 and 180 or so for the carbonyl. We might have our signal here for the methine that's next to the oxygen, and then we might have our other 3 signals down in the aliphatic range. So it might look something like that. Notice they're different sizes, even though most of them are going to cause 1 carbon. That's where we lose the integration of the carbon-13 NMR. Now the first depth experiment that we do is called the depth 45. Dr. O'Reilly, what do we see in the depth 45 experiment?
That shows everything except for quaternary carbons.
Yeah.
So the quaternary carbons are going to disappear, poof, but the rest of them will still be in the spectrum.
That's right. So basically, if the carbon has a hydrogen bonded to it, it's going to show in the depth 45. If a carbon does not have a hydrogen bonded to it, we call that a quaternary carbon, and then it won't show in the depth 45. So in this case here, if this one, say, was the two methyl groups, the clovers, I did draw that a little taller because it's being caused by two carbons, that one would show. And then the other aliphatic ones, for the other CH3 and the CH2, they would show as well. And then the one maybe for that's attached to the oxygen, the CH there, that would show. But the carbonyl out here that doesn't have any hydrogens attached.
And maybe it just makes sense for us to mark that here. So this is a C quat is what we refer to them as.
Yep.
So that one, Dr. Peterson was just saying, disappeared. It is no longer in the depth 45.
That's right. So by comparing the proton decoupled spectrum to the depth 45, we can tell which carbons have hydrogens, and more importantly, which ones don't. So in this case, the carbonyl carbon of the ester is the only one that doesn't have hydrogens attached, and its absence from the depth 45 would confirm that for us. The next depth experiment that we stack on top of that would be the depth 90. And the depth 90 is a pretty simple spectrum. It only shows carbons with a single hydrogen attached to them. So in our case here, the one with the single hydrogen attached is the one that's also bound to the oxygen, so we expect that one to be shifted a little further to the left. So possibly it's this one, and that would be the only signal that we'd see there. CH3s don't show, CH2s don't show, and C-quats don't show. Just carbons with a single hydrogen attached. Okay. So now we have evidence for our C-quat, our carbonyl, and our CH from comparing those different experiments. The last one.
135, yep.
Yep. Drop high here.
It's too tall for me. Good thing you're doing.
Yeah.
Good thing you're doing the video.
Worried about the shadow from the screen here.
You'll be okay.
This is called the depth 135. Smarter man would have planned ahead on this a little bit. But the depth 135 is probably the most complicated of the three depth experiments to interpret, but also the most informative to us. And all the information we get from the depths is generally by comparing them to each other as opposed from looking at the one by itself. So what goes on in the depth 135 is that CH3s and CHs are positive signals. And so what that means is they extend up from the axis of the spectrum. And so like this signal here, that's a CH, that would extend up. If I'm going to say that this signal here is my clover CH3s from the isopropyl group, that would point up. It would be taller, but I ran out of board space. And if I'm saying that this one here is that other methyl group, the heart one at the left end of the structure, that one would show here pointing up. CH2s in the depth 135 are negative signals. And what that means is they point down from the axis of the spectrum. So if we have negative signals there, that would indicate that that carbon is a CH2. Quaternary carbons don't show up in the depth 135.
Or any of the depths.
Or any of the depths. Yeah. And so what we have then by comparing these, so comparing the proton decoupled to the depth 45, we can tell which carbons lack hydrogens. They're quaternary. By looking at the depth 45, we can figure out which of the carbons that have hydrogens have only one hydrogen. And then by looking at the depth 135 and comparing it to the other two depths, we know which ones are carbons with a single hydrogen. The negative signals are carbons with two hydrogens, and then any remaining positive signals that weren't in the depth 90 are going to be your methyl group signals. So in this case here, we have the first signal is a methyl group because it is in the depth 45 and not in the depth 90 and in depth 135. The second one is also a methyl group for the same reasons. The third signal here is a methylene. It's in the depth 45, meaning it has H's. It's not in the depth 90, meaning it's not a CH. And then it's a negative signal in the depth 135, meaning it's a CH2. And then this fourth signal would be a carbon with one hydrogen. And it's in the depth 45, meaning it has hydrogens. It's in the depth 90, which means it has a single hydrogen. And then it also shows up as the positive signal in the depth 135. And then the signal out here that showed up in the decoupled spectrum, it doesn't show up in any of the others, would indicate that it's a quaternary carbon.
All right. All right, so now you got a pretty good detailed understanding of kind of, we'll say, you got an overview of what carbon-13 kind of adds to our basket of options with IR, mass spec, and proton NMR, how all those things can kind of be used together. All the stuff we talked about, though, or Dr. Peterson talked about, because I was just standing over there, all of the stuff we talked about is in the tutorial that you're supposed to work through. This is kind of one of those dry labs where you're working through that tutorial. It's going to have questions through the tutorial, so now it's time for you to take what you've seen here and turn back to the tutorial, dig into it, find questions. We're going to have a discussion board set up. There will be a forthcoming email telling you more about that. But essentially, we're learning carbon-13 NMR by this discussion board now, and there will be a report sheet that you will have posted on Canvas as well that you'll fill out once we've gone through that tutorial. So look toward that, and thanks for watching the video. We feel like a couple of movie stars over here. All right, bye.